All right, ladies and gentlemen, we're going to find all the zeros of a polynomial function. So when we did rational root theorem last time, we found the rational roots. Okay, so I need you to understand the difference. Rational roots are numbers we can comprehend. They include whole numbers like 2. They can include fractions like 1/2. They can include decimals like 0.3. They can also include negative numbers like -5. Okay? Those are rational roots. But sometimes when we are solving polynomials, we get other type of roots. And these type of roots are called complex roots or irrational roots. So here's a description of what a complex root is. But to put it simply, a complex root is when you get a square root that is a negative number. Okay? And in IM2, you should have been taught that we cannot take a square root of a negative number. It's impossible. But now we are going to start taking square roots of negative numbers, and they turn into complex solutions. And these solutions have a very unique answer to them. They have the answer I. So if I was going to take the square root of -4, what I would really do is get rid of the negative by turning the negative into what is called an imaginary solution. So in essence, the negative turned into I, and it's now gone away. We now can take the square root of 4, and the answer to this would be plus or minus, the square root of 4 is 2, but then we would associate it with an I at the end. And this is called a complex solution. It is an imaginary number. Okay? The other type of solution that you can have are irrational solutions. Here's a brief description of it if you want to read it. But irrational solutions, very similar to complex solutions, has a unique type of answer. For example, an example of irrational solution would be the square root of 7. The square root of 7, there's actually not a square root for that. It's some long, ridiculous decimal. So the square root of 7 is called irrational because the number we get is something we cannot really comprehend. It's a long number that has no just to give you an idea, when I punch the square root of 7 in my calculator, I get 2.64575, and it just keeps going. The numbers continue and continue. This makes it irrational. Okay? So these are type of solutions that we can have when we're trying to solve for a polynomial function. All right? The other thing I want you to understand is each one of these, when we get a solution like this, it's going to always come with a positive and negative answer. Just like in here, we had plus or minus 2i. For irrational, if we got a solution like this, the true solution is really plus or minus the square root of 7. Okay? And that's what this part is saying here. We're going to have two types of answers, plus answer and a minus answer. All right, let's go back and let's make something very clear. Maybe I wasn't that great on it in the previous set of notes, but what is a root? So a root, when we're talking about roots, there's many names for roots. So roots has multiple names. Another name for roots is zeros. So if I ask you to find a 0, I'm really asking you to find the root. Another name for zeros is solutions. So if I ask you to find solutions, I can ask you to find roots and zeros. It means the same thing. Another way we can say this thing is x-intercepts. okay? And what these things really mean is when we have a polynomial function, it is actually graphable. We can actually graph it. So if you look, here is an example of a graphed polynomial function, okay? If you're looking at the graph, it's actually really easy to see the solutions or the roots or the zeros or the x-intercepts. So I'm going to put in red the solutions to this particular graph, okay? So if you look, the solutions we get is these. Solutions or roots are basically where my graph touches the x-axis. So these are the solutions or roots. Let's not do it that way. Or roots or zeros of my function. They're also called x-intercepts. Okay? So this is basically when I'm asking you to solve a polynomial function, you are in essence trying to find where does this polynomial graph cross the x-axis. Okay? And these are considered rational answers. Answers we actually could comprehend. Now going back and just tying this in together, complex solutions will not show up on a graph. They are just not part of the rational solutions that we have here, as you will get to see in a little bit. All right, so I just thought I'd do a quick overview of what all this is going towards, but let's go ahead and move on, and let's actually find all the zeros of the next example, and this includes complex solutions and or irrational solutions and rational solutions. All right, let's find all the roots to example A. So if you notice on the left, I put my version of the steps on how to do solving for polynomial functions. But before we get started, I'm not going to read this to you. You can read it yourself. Before we get started, there's an important idea we have to know, okay? The highest powered variable, in this case, the power of 3, this highest powered exponent actually gives us a hint. It tells us how many solutions we should have. So in other words, how many answers we should have, how many zeros we should have, how many roots we should have. So when we're done, we should have 3 answers. All right, so that's a huge hint. Until we get those 3 answers, we're not going to stop doing these steps over here on the left. All right, so let's get started. So we're looking to find 3 answers, 3 zeros, 3 roots. So the first thing I want to do to solve is try to do the easiest thing first. I want to see if this function, this polynomial, can actually be factored. And if you notice, remember we're trying GCF, but we're done teaching factoring. So I'm going to go into and jump into what I know should factor. And we should be able to factor this by grouping. So I'm going to group and group. Okay, so we're grouping. The GCF of the first guy is x squared. And when I divide out an x squared, that gives me x minus 2. The GCF of the second guy is 5. When I factor 5 out, that's x minus 2. And what you'll notice is I can now, because these guys match, factor by grouping is going to work. So my answer is going to look like this. So again, this is factored form. Hopefully you can follow along. So my problem has now turned into this. Now, since I did step 1, I want to move on and see if I can solve these things. If I cannot solve these things, then I would have to move on to quadratic formula. And if quadratic formula doesn't work, then I would move on to rational root theorem. But it's going to be up to you to start noticing that these are actually solvable. When you're left with only one x in your factors, we can solve them. We're pretty much done. Okay? So to solve these things, to solve by factoring, what we did last time is we took each one of these and we simply put them equal to 0. So when it's totally in factored form, we want to put it equal to 0. Again, the rule is, when do you know to put it equal to 0? Is when your factors have one x left over. Okay, that's kind of how I do it. And you should be able to factor that point. So we're going to solve this x first because it's simpler. I'm simply going to add 2, and we get x equal to 2. This one, again, this is IM1 type problems. I'm going to subtract 5, and we get x squared equal to negative 5. And now, thinking of your algebra skills, I want to solve for x. So to get rid of the power of 2, hopefully you remember that we are going to square root both sides. And what happens is the power of 2 and the square root cancel each other out. So x is equal to the square root of negative 5. And hopefully now you recognize that this is actually, we cannot do this. This is going to be a complex solution. We cannot take the square root of a negative. So what we have to do is turn that negative into an imaginary I. So this is going to be I times the square root of 5. And because 5 also is irrational, 5, if you put the square root of 5 into your calculator, it gives you this long digit. We don't want that. So this is actually my final answer. But what you have to remember, anytime you have an imaginary answer or an irrational answer, your answers always have to have two answers, a positive and a negative answer. So if you look here, our final answer is this. We should have a total of 3 answers, because that's what our power is. So I have to write this out. So my first answer is a number we can easily comprehend. It's 2. My second answer is going to be I square root of 5. And then my third answer is negative I square root of 5. And there we go. We now have 3 answers. So it's very important to remember, anytime we're dealing with a complex answer like I or an irrational number, something that cannot be square rooted, there's always a positive and negative. These are called conjugates. All right, let's go ahead and do an example B. So in this example, again, we're trying to find all the roots or zero solutions, all that good stuff. So the first thing we want to try to do is factor if possible. For time's sake, I'm letting you know factoring is not an option. It also does not quite qualify for quadratic formula, so we got to jump down to rational root theorem. So let's go ahead and do that. So rational root theorem says take your constant, 15, your leading coefficient, 1, and these are all the factors of my constant, the top number. These are all the factors of the bottom number. Now let's create our possible solutions. So again, the rational root theorem, our possible solutions are taking the top number divided by the bottom number. If you do that for all combinations, this is our possible solutions. So now let's go ahead and do synthetic division to figure out which one of these is a possible root or zero. So synthetic division, we'll take our coefficients without skipping power. So we have 1, negative 7, 17, and negative 15. And the first option I want to try is our first possible solution. I'm going to try positive 1. And our goal is to get 0 here. If we don't get a 0, then we got to choose another possible solution. So let's go through the work. Bring down the 1, that gives me 1. Negative 7 and 1, that's negative 6. That's negative 6. That gives me positive 11. And that gives me positive 11 here. It's not going to equal 0, so that means 1 is not the solution. So let's redo this, and let's try now negative 1. Negative 1 times 1, that's negative 1. That gives me negative 8. Negative 1 times 8, that is positive 8. 17 and positive 8, that's going to give me 25. And this gives me negative 25. As you can see, negative 1 does not work as well. So we got to move on to 3. So, all right, let's try 3. So bring down the 1. Oops, that gives me 1. 3 times 1 is 3. It's negative 4. That gives me negative 12. That turns into 5. 3 times 5 is positive 15. And we have found our answer. It is 3. Okay? So now, let's rewrite. So this 3 turns into the polynomial of, switch the sign, x minus 3. And then we rewrite using these coefficients here with 1 less power. So that's going to be x squared minus 4x plus 5. And now we start this whole process again. So let's go back over here. And then we're going to try to factor these if possible. We know this is not factorable. We're going to try this with diamond method. So let's try diamond method. That gives me 5 on top, negative 4 on the bottom. What multiplies to 5? That adds up to negative 4. And that is going to be negative 5 and 1. So let's factor this guy. Sorry, that's incorrect. Negative 5 and 1 does not give me positive 5. So as you try this, so we only can use 5 and 1, but it has to add up to negative 4, and actually diamond method will not work. Okay, so we're looking back at our steps here. Diamond method didn't work. So we go to part 2, see if we could solve it this way. Is this a quadratic that we can use a quadratic formula on? And the answer is yes. So we're going to use quadratic formula here. Again, we're going to ignore x minus 3 for now. We'll solve him later. We're going to focus in on this, and we're going to use quadratic formula. Okay, so again, this is from IM2. We need our A value, our B value, and our C value, including the sign. So A is 1, B is negative 4, and C is 5. And we're plugging it into this guy. Let's see if you guys recall this. B squared minus 4AC all over 2A. Okay, so let's plug this in. We have negative b, which is negative 4 plus or minus the square root of b squared. That's going to give me negative 4 squared minus 4 times a, which is 1, times c, which is 5, all divided by 2 times 1. Okay, now let's work this out. I like to clean up the square root stuff first and just focus in on that. If you clean it up correctly, we get negative 4 squared is positive 16, and negative 4 times 1 is negative 4 times 5. That gives me negative 20. And we end up with negative square root of 4, and then we'll do the other math. Negative times negative 4 for this guy here. This turns into positive 4 all over 2. Okay? So I'm going to continue this over here. So now we have 4 plus minus square root of negative 4 all over 2. We want to clean up the square root of negative 4. Remember, this is a negative square root, which is unable to do, so we got to turn this into a complex answer, which means there has to be an I here. So 4 plus or minus I, and that gets rid of the negative, so now I have 4 over 2, and now I can do the math. So it's going to be 4 plus or minus, the square root of 4 is plus or minus 2, and the I goes along for the ride all over 2. And again, from IM2 you should know that this actually splits into 2 problems. So it's 4 plus 2i, so we basically just take one of the signs, all divided by 2, and it's 4 minus 2i, all divided by 2. And we want to clean this stuff up if we can. So, for example, 2 can divide both of these. Okay, so I'm going to divide 4 by 2 and then 2 by 2. So if we get that, this turns into 4 divided by 2. 4 divided by 2, that gives me 2. And then 2 divided by 2, that gives me plus 1i. Okay, same idea here. 4 divided by 2, that gives me 2. And then negative 2 divided by 2, that gives me negative 1i. So we cannot clean this up no more. These are actually 2 of our solutions. These are actually, we would put them equal to x, because that's what the quadratic formula does. It solves it for you when you cannot factor. So that's 2 solutions, but recall, how many answers do we really need? If we look at our power, we need 3. We have 1, 2, and we get the third one from over here. We can't forget about this part. So we're going to put him, he's factored all the way through, we're going to put him equal to 0. So if we solve for x minus 3, so we have x minus 3 equal to 0, add 3 to both sides, x is going to be equal to 3. And now we have our solutions. We have 2 complex solutions and 1 rational solution.